Hi everybody, this little video here is going to help us with the properties of logarithms, and I wanted to make a couple of statements right up front here about these properties of logarithms. First one is that they are kind of like the laws of exponents, but I'm not going to make any direct connections or parallels between specific laws of exponents because that can actually lead to some confusion. Another thing to get up front here is that the reason we have these properties of logarithms is so we can expand or simplify expressions. Expand means to basically break apart a complicated log statement into its smaller components, and simplify is kind of the opposite of that. We'll take a sum or difference of log expressions and combine or simplify them into a single logarithm. And then the other thing is that all these log properties go on some basic assumptions. All right, these assumptions are something like this. For a statement such as log base a of b, and that's how you read that statement, by the way, is log base a of b. The first assumption is that the a is greater than 0 and not equal to 1. Okay. The second assumption is that b is a number greater than 0. And one more thing is that the b there is called the argument of the log expression. Okay? Great. Okay, so we will get started with our first log property, which is the log of a times b is equal to the log of a plus the log of b. In other words, log of a product is equal to the sum of two logs. Okay? Log of a product is equal to the sum of two logs. Here's an example of that. Log of 6x, we could rewrite that as log of 6 plus log of x, because 6 times x is a product. Of course, the rule, just like the rules of exponents, work both ways. So you could simplify a sum of two logs, such as log of 2 plus log of 5. You could write that as log of 10. Which, in this case, actually does simplify just a little bit further, doesn't it? What's log of 10? Log of 10 equals 1. So the next log property is kind of the inverse of that first one. Log of a over b is equal to the log of a minus the log of b. In other words, the log of a quotient is equal to the difference of logs. Okay? Let me give you an example of that. Here's an example. Log of x over x minus 1 is equal to log of x minus the log of x minus 1. So you can see very clearly it fits the pattern. Log of a quotient is equal to the difference of two logs. This example actually brings up something else that's very important, so I'm going to take a moment just to diverge a bit from log properties and talk about this. We have here clearly a function of logs. It's not just log of 3 or log of 5 or something like that. Log of a real number. This is a log of a variable, log of x, a function of x. And anytime we have a function of x, one of the most important things we need to be aware of is the domain of that function. What values can we use for x? Well, a little bit earlier, we saw that when I used the expression log base a of b, that b, calling that the argument of the function, b had to be greater than 0. So the argument has to be greater than 0. That's just as true for a function as it is for log of a real number. So that's true, and you could figure out what the domain of x over x minus 1 is, and to make that a positive number. But notice that on the right side of this equation we have log of x minus the log of x minus 1. Those are pretty easy to figure out, right? The domain of log of x is just x greater than 0, because the argument has to be greater than 0. And log of x minus 1 is also pretty easy to figure out. The domain of that is just simply x greater than 1. Well, if we remember something from combining functions together, in this case we are combining two functions by subtraction. And anytime we combine two functions together, the domain of that combination is the intersection of the two domains of its parts, in this case 2. So if we look at the domain x greater than 0 and the domain x greater than 1, the intersection of those two intervals, in other words, here's interval 0 to infinity, or x greater than 0, and intersection that with 1 to infinity, all we have to do is figure out what that is. And think about that for just a moment. 1 to infinity is actually a subset of 0 to infinity. The overlap, or the intersection of those two intervals, is simply 1 to infinity. So that's the domain there of the combination of log of x minus log of x minus 1. Therefore, that's the domain of our original function there, x over x minus 1. So there's the domain. Notice also one thing about something else a little bit different about this. I have a log of x minus 1 here. All right? That does not simplify at all. All right? There are no rules for simplifying a log of a difference. The two rules we've seen so far are log of a product and log of a sum. Those equate to each other. And log of a quotient and log of a difference of two things. Those equate, and a difference of logs. Sorry, I said it backwards. A log of a quotient and a difference of logs. Okay? So we have a log of a product and a sum of logs, log of a quotient and a difference of logs. I think I said it right that time. So a very important point there about these log properties. Okay, we're going to move on to the next property now. Alrighty, here well the third and final log property that we're going to look at is this very important rule here. Log of a to the c is equal to c times log of a. So the exponent here of c becomes a multiplier, a coefficient of the log of a. Very interesting situation here. Here are a couple of examples. We'll use natural log this time. So natural log of x squared could be written as 2 times the natural log of x. Pretty simple application of this property. Let's turn it around like we have with the other properties. Here's something. 1/3 of the natural log of x plus 1 is equal to the natural log of the cube root. So think about that for a second. If you move that 1/3 over here as an exponent of the parentheses x plus 1, that's the same as the cube root. So we can write use this using radicals also. Also notice that natural log of x plus 1 does not simplify or break down at all. The log of a sum is just the log of a sum. It does not split up or simplify. Let's do another example here. Negative natural log of 2. Okay? Well, what are we multiplying there by? We're multiplying by negative 1. So it's like negative 1 times the natural log of 2. All right, so let's write that as natural log of 2 to the negative first. Okay, well, what's 2 to the negative first power? Right, 1/2. So negative natural log of 2 is equal to the positive natural log of 1/2. Kind of interesting there. So we are going to finish that up there, and what I wanted to speak to you next is about combining log properties here. Okay, so I want to show you how these different log properties can be combined and how you can kind of unwrap or compact things together. Alrighty? So the first example I would like to show you here is using natural logs again. Natural log of the square root of 3x. Alrighty, well, first let's bring that radical as an exponent. So let's rewrite it as natural log of 3x to the 1/2 power. Now we can bring that exponent down as a coefficient and write it as 1/2 times the natural log of 3x. Aha, but 3x is a product. So we can split that up into a sum of logs. So 1/2 times natural log of 3 plus natural log of x. Okay, so that's combining a few different rules there. Let's look at another example. Here's, well, I got the whole thing spelled out for you right here. Log of this big old fraction, x cubed over 2 times x plus 1. All right, first we'll split that up into log of x cubed minus log of 2 times x plus 1, because that's a quotient, so we can write that as a difference of logs. But there's an exponent there, so let's bring the exponent 3 down. So we have 3 times log of x minus, and then notice that 2 times x plus 1 is a product, so I'm writing that as a sum of logs, log of 2 plus the log of x plus 1. But we're subtracting that right there. Alrighty? So there's that one. Let's do one more example. Let's see, this is going to look like this. Here's our last little combining log properties slide, and I'm going to write out this big thing right here. 1/3 times the natural log of x minus the natural log of y plus 2 natural log of x plus natural log of y. So first let's combine the two things inside the big parentheses there, the difference of those two logs, as a quotient. All right? So that's going to look like that. Next, we've got 2 natural log of x, so let's write that as natural log of x squared. And then we have natural log of y, so we'll just put that in there. Now let's combine use the power rule there with the exponent, bring that 1/3 up, so we have natural log of the cube root of x over y, times, because we have a sum now, a sum of logs, so we can write that as a log of a product. So natural log of x squared becomes just times x squared, and then times y. And so basically the whole thing simplifies to this. When you actually use all your laws of exponents there, and I'm going to leave that up to you to finish up the final details of that, but this is what you'll end up with: natural log of x to the 7/3 times y to the 2/3. Okay, well, enjoy all your symbol manipulation exercises with log properties. It actually is kind of fun once you get the hang of it. So long.